This is the harmonic oscillator video, and this is an air track. See these little holes? The air comes up there and blows into them. And this is a mass over here. This is the mass, and this is a stationary thing. So notice this loop of wire. This loop of wire represents the spring. This is what makes the thing oscillate. And when you stretch it out, that increases the potential energy of it to move back and forth. And when it goes this way, it's going to compress, and then that'll increase the potential energy in the other direction. So the force is going to be opposite which way you're going, and that will help this thing oscillate. Now let's see if we can watch this thing work. There you go, it's oscillating back and forth. And that essentially is this whole thing we want to analyze with Newtonian mechanics. And after we complete analyzing it with Newtonian mechanics, we'll look at a quantum mechanical picture of this whole thing. Here's a similar setup: weight, spring. You pull the weight this way from its rest position, and the force is trying to push it to the left. You compress the spring, and the force wants to push it to the right. Right is positive, left is negative. So let's see what happens here. The force is equal to X times a spring constant. And the negative sign is because it's in the opposite direction of where the weight is pulled. So we've got a force. So we're doing this with Newtonian mechanics, so we can figure stuff out with forces. We don't have to go to the Schrodinger equation, which we'll do in a while, but not right now. Let's try to figure out what kind of function can represent this oscillating movement back and forth. The old classic F equals ma. And if we put this in a form of an x, that's going to be m times the second derivative of x with respect to time. But what's f? F is a function of x minus kx. So I'm just going to put minus kx equals m times the second derivative of x with respect to t. We can put this into a differential equation by saying that second derivative of x with respect to t, x is a function of t here, equals, and instead of negative kx, it's going to be negative k over m. This is the differential equation that we're trying to solve. And I'm going to propose that if we watch that weight going back and forth and back and forth, that could be just a simple wave function, and I'm just going to choose the simplest wave function, sine function. And the sine function has to be a function of t, and I'm going to do it this way: omega t. Sine of omega t. Now the question is, why do I think this is going to work? Well, if we take the first derivative of sine, and I'll just call that my x function, that's going to equal cosine omega t times omega. And I'll put this parentheses around here so you can see that that's the angle. If I take the second derivative, respect to t, what do we get out of that? Remember, x is a function of t. We get negative sine omega t times this other omega times the next omega gives us omega squared. That was minus omega squared times sine omega t. We also had this, which is what we used as another starting point. That was equal to negative k over m times x. Well, sine omega t is x. The omega squared has to equal this km. Omega has to equal square root of k over m. This is the angular frequency of the oscillation of that. And that means that the tighter the spring, the faster the oscillation. The more mass that you put, the slower the oscillation. So some of that should make some sense. All right, there's a lot of stuff that I added here. And this is all to figure out the big V, which is the potential energy with respect to X. And remember, that's what we need when we talk about the quantum mechanics analysis of this whole mess. Now I'm going to put absolute value around this because the potential energy can't be negative. You can't have a negative energy. So let me plug this thing in here. And what I'm doing is saying that negative kx, which is the force, times the distance, which the distance is going to have to be integrated over that interval from 0 to x as we stretch that spring out. And if you look at this thing using the exponent rule when you're talking about integrals, that's going to be x squared over 2 as a result of this integral. So how do I place that in? The absolute value makes it positive, so that equals 1/2 k squared. But remember what we have up here that says that omega squared equals k over m. So if I transpose this thing around, that's going to be k equals m omega squared. Now I'm going to plug that in. Now, what do I want to do that for? Well, I'll tell you what. In quantum mechanics, if we're talking about a diatomic whatever that oscillates, in the atomic world, which is what the whole purpose of this video is to examine the atomic world, there's no such thing as a spring constant. There's not an actual spring. There's forces at play that create that situation. So this is the way I'm going to represent the potential energy when I talk about the quantum mechanical version of this whole thing. Okay, this should look familiar to you. This is the full Schrodinger equation. I times h bar first partial of psi with respect to t is equal to this whole mess here, which is this is the time dependent, this is the time independent because there's no t over here. That's negative h squared partial blah blah blah. This 2m is down there for good. And there's the potential energy that we just developed last time. So I copied the whole thing over. Here's the potential energy. And shows really what we want to focus on. The energy times the psi function equals this time independent Schrodinger equation times psi, which is a function of x and it's a function of t. It seems like we would need that function of t because this is an oscillator and things are changing over time. Now, how do we solve this thing? How do we solve it? Well, research shows that the derivation of this equation ain't that simple. So what I'm going to do is switch over to a reference source, quantum harmonic oscillator, and I have this little pen thing that allows me to draw on the screen to fix something. Let's see if we got, let's choose blue, and I'm going to put, or maybe put red so that we emphasize that there's a screw up here. This should be squared. So even remember, when you do a text, it's not necessarily perfect. They can make mistakes there. So go back to my pointer here. H squared, that should look familiar to you. There's the psi of x, and this is the energy. If we solve for the energies, this is the way it comes out. Okay, hocus pocus, here's the magic result, but how did I get there? Well, and here's the n values. So n equals 0 would be the ground state energy or the ground state harmonic oscillator. And then all these other things happen from there. What a complicated psi function. Look at all that beta x squared h sub n. What's the h? H is the Hermite polynomial. What in the heck is that all about? So all these things go together so that you start seeing that things are getting really complicated. And if we do the quantum mechanical picture, which is probably why people don't even want to touch it. And you take a physics course and you say quantum mechanics, forget about that. There's no way I'm going to do that. So I'm just kind of buzzing through this so you won't get lost, and we can look at the math derivation of all of this once I figure it out. Now, these are some different, let's go ahead and read this. I'll go ahead and read this aloud to the class. The first 5 wave functions of the quantum harmonic oscillator. The classical limits of the oscillator's motion are indicated by vertical lines. Vertical lines, let's see what that means. The classical limits. Classical limits. Notice that the classical limits, once we go to some of these higher wave functions, they go beyond the classical limits. So that means that we are, let me get rid of that squared thing there. That means that things go beyond, like for instance, this classical limit, went beyond that. But that kind of makes sense in the quantum mechanical world because position doesn't have a real localized situation. It's a wave function and probability through space. So I assume that's very similar to that. And let's see, let's keep reading on here. corresponding to the classical Turing points at x equals plus or minus a. A, capital A, is the amplitude. Got to get it out. Amplitude of the sine function with the same energy as the energy of a quantum oscillator in the state indicated in the figure. That's probably enough for now. Hello. Exhaustion from all that stuff that I just talked about. Please comment on this if you want to go through the derivation of all that stuff. Also, comment if you don't want to go through the derivation of all that stuff and you want to move on so we can get to the hydrogen atom. I think the second choice is the route that I will take.